Class, in our last lesson, we studied concrete durability. Today, we are moving into the core of concrete engineering practice, concrete mix design. The mix design directly determines concrete strength, durability, workability, and cost-effectiveness, making it the foundation for subsequent engineering practice. I hope you can follow the reasoning closely and focus on mastering the core logic and methodology. There are two main focuses in this lesson. First, the requirements for mix design, and second, the design methods. Among these, the design methods are the key point and must be thoroughly understood. Let's approach this lesson with 3 questions in mind. First, let's clarify the concept. A concrete mix is the mass ratio of each constituent material per unit volume of concrete. For example, to prepare 1 cubic meter of concrete, the actual quantities of each material are 295 kilograms of cement, 648 kilograms of sand, 1,330 kilograms of coarse aggregate, and 165 kilograms of water. Based on the mix by weight, the ratio of cement to sand to aggregate is 1 to 2.2 to 6.51, while the water to cement ratio is 0.56. A mix design must satisfy 4 basic requirements. 1. Meet the strength grade specified in the structural design. 2. Have the workability required for construction. 3. Meet the durability requirements for the engineering environment. 4. Follow economic principles, conserving cement to control costs. The water-cement ratio, unit water content, and sand ratio are the 3 fundamental parameters of concrete mix design. Regardless of the method used, the design ultimately revolves around these 3 parameters. Before diving into each parameter in detail, let's take a macro view of concrete's composition and structure. As shown in the diagram, on the left, cement and water combine to form cement paste, which serves to coat and lubricate the aggregates. On the right, sand and coarse aggregate make up the aggregates, acting as the framework that provides strength and stability to the concrete. When the cement paste and aggregates are mixed, we get the concrete we need. Understanding this structure of paste wrapping the skeleton helps us grasp how these 3 parameters work. Let's start with the most important parameter, the water-cement ratio. As the name suggests, it is the ratio of the mass of water to the mass of cement and primarily determines concrete strength and durability. We can make an analogy. The hydration reaction of cement and water is like kneading dough. Part of the water is consumed in the reaction, while the rest is excess. A higher water-cement ratio means the cement paste is more diluted. This reduces its bonding ability, making the concrete skeleton less dense and naturally lowering strength. At the same time, when the excess water evaporates, it leaves behind pores and channels, which allow corrosive agents like chloride ions and carbon dioxide to penetrate, causing reinforcement corrosion and significantly reducing durability. Therefore, while meeting workability requirements, we should always aim to minimize the water-cement ratio. This is the primary prerequisite for achieving high-strength, high-durability concrete. Next, let's focus on the second parameter, the unit water content. This refers to the amount of water required to prepare 1 cubic meter of concrete and primarily controls the workability of the fresh concrete, that is, its consistency or flowability. The more water added, the more fluid the mix becomes, and the better its workability. But be careful. Not unlimitedly increasing water to improve flowability, because this directly raises the water-cement ratio, sacrificing both strength and durability. To achieve good workability while keeping a low water-cement ratio, water-reducing admixtures come into play. They can effectively improve flowability without increasing the total water content. Now let's look at the third parameter, the sand ratio. The sand ratio is the percentage of sand by mass in the total aggregate, and it primarily affects the cohesion and water retention of the concrete. We can think of sand and coarse aggregate as a team. The coarse aggregate is the main force providing strength, while the sand acts as the filler and liaison. If the sand ratio is too low, there isn't enough mortar to fill and lubricate between the coarse aggregates. The mix becomes rough, prone to segregation and bleeding, with coarse aggregates sinking and paste rising, which can lead to honeycombing and surface defects after casting. On the other hand, if the sand ratio is too high, the total surface area of the aggregates increases, requiring more cement paste to coat them. With a fixed paste amount, the coating becomes thin, making the concrete dry, less workable, and uneconomical. Therefore, the goal is to choose a sand ratio that just fills the gaps between the coarse aggregates while leaving enough excess to act as lubrication. The logic becomes perfectly clear when we look back at this figure now. The water-cement ratio controls the quality of the cement paste, determining the depth of strength and the breadth of durability. The unit water content controls the quantity of the cement paste, determining workability during construction. And the sand ratio coordinates the proportion between the skeleton and the filler, determining concrete stability and cohesion. These three parameters are not isolated, they are interrelated and mutually constrained. A skilled mix designer is like a symphony conductor, carefully balancing these three parameters to create concrete that is strong, durable, workable, and cost-effective. These three fundamental parameters form the foundation for all subsequent calculations and design steps, so it is essential to understand them thoroughly. Next, let's look at how to apply these parameters in practice for mix design. There are two main methods for concrete mix design, the volumetric method and the mass method. The volumetric method calculates the mix based on the principle that the sum of the volumes of all materials equals the volume of concrete. The mass method assumes a total concrete mass and then back-calculates the required amounts of each material. A mix design must satisfy four basic requirements: strength grade, workability, durability, and economy. Among these, the water-cement ratio, unit water content, and sand ratio are the three key parameters. Now, let's go through the step-by-step process for calculating a concrete mix design. Step 1. Calculate the target strength for construction. Estimate the required concrete strength using empirical formulas. Step 2. Calculate the water-cement ratio based on the target strength. There is a statistical relationship between water-cement ratio and concrete strength, which allows us to calculate the required water-cement ratio. Key point: after calculation, check durability. The water-cement ratio determined from strength must not exceed the maximum value specified in the standards. If it does, the durability will be insufficient, and the standard limit should take precedence. Step 3. Determine the unit water content. When the water-cement ratio is between 0.40 and 0.80, the unit water content can be selected from standard tables based on the type and size of coarse aggregate and the target slump. If the water-cement ratio is outside this range, or if special forming techniques are used, it must be determined through testing. According to current standards, the unit water content for plastic concrete must meet specific requirements depending on the desired slump. For dry and stiff concrete, determine the maximum usable size of gravel and crushed stone by measuring the BB consistency. When admixtures are added, the unit water content can be calculated using the following formula. Multiply the unit water content without admixtures by the water-reducing coefficient, which is determined through testing. Step 4. Calculate the amount of cementitious materials. Divide the unit water content by the water-cement ratio. After calculation, check durability. Compare the calculated value with the minimum cementitious material specified in the standards, and take the larger value as the total cementitious material. Then, determine the quantities of cement and supplementary materials, such as fly ash, according to the specified proportion of mineral admixtures. Step 5. Determine the sand ratio. For concrete with a slump of 10 to 60 millimeters, select the sand ratio from standard tables based on the type and size of coarse aggregate and the water-cement ratio. For slump greater than 60 millimeters, determine by testing or increase the sand ratio by 1% for every 20 millimeters increase in slump on top of the table value. For slump less than 10 millimeters, testing is required. Specifically, select values according to the ranges in the standard tables corresponding to the water-cement ratio, type of aggregate, and maximum particle size. Step 6. Calculate the quantities of sand and coarse aggregate. There are two methods. Let's start with the volumetric method. Volumetric method, core principle. In 1 cubic meter of concrete, the sum of the volumes of cement, sand, coarse aggregate, and water equals 1 cubic meter. Using the sand ratio, we set up equations to solve for the masses of sand and coarse aggregate. Mass method, also called the assumed bulk density method. First, assume the total mass of 1 cubic meter of concrete mix. Then, using the total material mass and sand ratio, set up equations to solve for the masses of sand and coarse aggregate. So, how do we calculate the trial mix design? First, based on the calculated mix, we weigh out the required quantities of each material and prepare 15 liters or 25 liters of concrete. Then, we measure its workability and strength. Next, conduct a slump test on the reference mix and check its cohesion and water retention. If the measured slump is lower or higher than the design requirement, keep the water-cement ratio unchanged and adjust the amount of cement paste accordingly. If the mix shows poor cohesion or water retention, the sand ratio can be slightly increased. After each adjustment, remix and retest until the requirements are met. Record the adjusted material quantities and measure the actual bulk density of the concrete mix. Typically, 3 different trial mixes are prepared. One is the reference mix, and 2 others with the water-cement ratio increased and decreased by 0.05 relative to the reference. The unit water content remains the same as the reference mix, but the sand ratio can be slightly adjusted and the bulk density measured. For each mix, prepare 2 sets of strength test specimens, cure them under standard conditions for 28 days, and then measure the compressive strength. Based on the relationship between strength and water-cement ratio, use a graphical or computational method to determine the water-cement ratio corresponding to the target construction strength. Adjust the unit water content according to the slump or VD consistency of the trial specimens. Cement content equals unit water content times selected water-cement ratio. The sand and coarse aggregate quantities are adjusted from the reference amounts based on the selected water-cement ratio. Using the material quantities determined in the previous step, calculate the concrete's theoretical bulk density according to the following formula. Then, compute the mix correction factor. If the absolute difference between the measured bulk density and the calculated value is within 2% of the calculated value, the mix from the previous step is the final design mix. If the difference exceeds 2%, multiply the quantities of all materials in the mix by the correction factor delta to obtain the final design mix. Unlike in the laboratory, there are also corresponding calculation methods for use on construction sites. First, since the sources of sand and coarse aggregate vary by location, we need to measure their moisture content before use. Let the sand moisture content be A% and the coarse aggregate moisture content be B%. Adjust the water content based on the on-site moisture content of the sand and aggregate, denoted as A% and B%, respectively. The quantities of each constituent material per cubic meter of concrete in the adjusted field mix can be calculated using the following equations. After covering laboratory and site mix design, let's move on to exercises and solutions. Step 1. calculate the target construction strength. For a C30 strength grade, the nominal strength is 30 megapascals. If no statistical data are available, assume a standard deviation of 5 megapascals and use the formula to calculate the target strength. Step 2. Determine the water-cement ratio and check durability. Calculate the water-cement ratio based on the target strength and ensure it does not exceed the maximum value specified in the standards. Step 3. Determine the unit water content. For medium sand and crushed stone with a maximum particle size of 40 mm, refer to the standard table and select unit water content MW0 equals 175 kilograms per cubic meter. Step 4. Calculate the amount of cementitious materials. Calculate based on the water-cement ratio and unit water content. Then, check durability. For this environmental exposure class, the minimum cementitious material is 280 kilograms per cubic meter. Take the larger of the calculated value and the minimum, in this case 350 kilograms per cubic meter, as the total cementitious material. Then, calculate the quantities of cement and fly ash according to the specified fly ash proportion. Step 5. Determine the sand ratio. For medium sand and crushed stone, 40 mm, with a water-cement ratio of 0.50, refer to the standard tables to find a sand ratio range of 30% to 35%. Select beta S equals 34%. Once the sand ratio is determined, calculate the quantities of sand and coarse aggregate. Set up equations using both the volumetric and mass methods and solve using the given parameters. Result explanation. The sand and coarse aggregate quantities calculated by the two methods differ slightly, but both are reasonable, and the final reference mix is determined based on these results. The key point for site mix design is the adjusted water content. Since site sand and coarse aggregate differ from the laboratory materials, their moisture contents must be measured. Based on the on-site moisture content of the sand and aggregate, denoted as A% and B%, respectively, the water in the mix is adjusted, allowing calculation of the quantities of each constituent material per cubic meter of concrete in the adjusted site mix. In today's lesson, we have answered the 3 questions introduced at the beginning, focusing on the 3 core parameters: water-cement ratio, unit water content, and sand ratio, and outlined the full process of concrete mix design. Please review today's content and complete the after-class exercises, reflecting on how adjustments to these parameters affect concrete performance in mix design. Class, in this lesson, we have systematically studied the requirements for concrete mix design, the core parameters, the 2 design methods, and the conversion between laboratory and site mixes, reinforcing practical logic through exercises. Concrete mix design is a core technology in concrete engineering, directly affecting project quality and cost. I encourage you to review the workflow in your homework and consolidate the key points. That concludes today's lesson. Thank you all for your attention.